So for my coding Kata demonstration today, I thought I'd want to get into an algorithm because there have been some questions about how you can kind of develop an algorithm through test-driven development. And I have a suggestion here. I want to see what people think about it. So to get into it, suppose you want to solve a maze. And we actually have a maze-solving contest coming up next week. If you're interested in that, it's on Thursday at Polo. You want to find the shortest path from a starting point to the goal. And there are a few different ways to do that, but a really simple way that you might think of yourself if you tried to work this out is called Dijkstra's algorithm. The way it works is you put a 0 on the goal, and you kind of work up from there, putting a 1 next to it. That means that point is a distance 1 from the goal. So the next point is a distance 2 from the goal, and keep working up to there. Now, after here, it kind of diverges. So you have to label all of the nodes next to the 4 with a 5. Both of those points are a distance 5 from the goal. You keep working outward. Does this make sense to people? All right. Keep working all the way outward. You get some 8s and 9s. And it doesn't really do anything interesting until you kind of get around to, well, we've already gotten to the start. So if we really were at the start, we could stop here, but let's finish this up and label the whole maze with all the distances to the goal. So there are these two 11s. They kind of intersect into a 12. It doesn't really make a difference. You just stop there. You're only labeling unlabeled spots with the distance. So when we finish that, we've now labeled every point with the distance from that point to the goal. And that means if you want to get from any point to the goal, all you have to do is follow the nodes with the lowest numbers. So if we start at the start, which is labeled at 11, see a 10 right next to it, and then follow that to the 9, and the closest node from there is an 8, and you end up just counting down 11, 10, 9, 8, 7, 6, 5, blah, 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 all the way down to the goal. That solves the maze. All right. So expressed kind of line by line as an algorithm, this is a simplified version of what's called Dijkstra's algorithm. You start with a list of all of the nodes in your maze, all of the points that you could be at, mark the goal with a 0, and then go into a loop until you've used up all of those nodes. Start by finding a node with the lowest score and label all of its unlabeled neighbors with that score plus 1. So that means you do all of the 5s before you do the 6s that you're creating as you are going through this process. And then once you've done that, you remove that node from the list and you proceed, because you've already labeled it and marked it, so you just keep going from there. So that's what we're going to do as a Kata. But I've got an empty Kata here. I'm going to start up guard. And since I know what my overall goal is here, I want to start just by writing kind of a feature test for the actual ultimate result. So let's say we have a really simple maze. This is kind of the simplest one I could think of. A connects to B, connects to C, or C connects to D. And just to make it a little bit more interesting, I'm going to put a connection here. Imagine that B also connects through D. This is like the simplest possible maze that is not totally trivial. So we're going to have a method on here eventually called solve. Oops, not off to a good start with this phone. And what should that do? Well, solves an maze, so I guess it labels the distances to a goal. So it'll be something like maze.solve should equal, well, so we have to specify what the goal is. So let's say we're going to point D. We're going to want it to give us the distances. And if you just look at it, it's pretty obvious. A, you only have to go 2 steps from A to the goal. B is directly connected, C is directly connected, and D is the goal. So that's what we'd expect. And of course that fails. So what we always do in these katas is start by implementing it in a really trivial way. Oh wait, look at the failure. Undefined variable maze. We haven't even set up the test correctly. So how do we make a maze? Well, we need to have some concept of what the nodes are. So I'm going to make an array of nodes. and we need the connections between the nodes. I figured I could represent that with a hash. So A will map to what it's connected to, which is just B. B is connected to all the other ones, so A, B, and C. Oops. Thanks. C is connected to B and D. And then D is obviously just connected to B and C. And then we would make the maze a little more closer. So then the maze, we have to make using the nodes and connections. All right, let's see what's going on.
You need a parenthesis.
Okay, so now we have a wrong number of arguments because we haven't defined an initialize method. So let's do that. So it's good. Maze takes nodes and connections. And I know I'm going to need these later, so I'm going to just make an outer accessor for nodes and connections and stick those variables right in there now. All right, so now we should get a different failure, which is that there's no method solve. So we got to create the method solve. And we know it's going to take a goal as an argument, which is the name of the node that we're looking for. So now we have a real failure finally. It's expecting to get this particular solution to the maze, and it just got nil because solve doesn't actually do anything. So now we do the thing that we always like to do here, which is just solve it in a trivial way to make sure we can. Now everything's passing. So we think we have a good algorithm here right now. Let's give it a more challenging problem by having two different tests. See if it can see if this code can solve the distances to the goal A. Well, let's work that out again. A itself is a distance 0 from A. B is 1 step away from A. And then C is 2, and D is also 2. So that's the answer we should get if we want to solve for distances to A. And of course that fails because we're not actually doing anything. We're just returning the same answer every time. So this is not going to work. We got to do something better. And what do we do? Well, here's my suggestion. We have this, we know the algorithm. We don't need to develop it. We know what it is. So I'm just going to write it down. We're going to start with a list of all the nodes. So I'll say unchecked nodes equals nodes. Mark the goal with 0. I'm going to abstract that out. So we're kind of building up this list of distances to the end. So I'm going to say that the distances are equal to some initial distances that I will have to define later. And then there's this while loop, which I think I can write as until unchecked nodes dot empty. We're going to do this stuff that was in our ABC here. So first we find the node with the lowest score. So again, I want to abstract that. It's going to be some method called, I guess it's closest. So I'll say closest node equals closest. And what do we need to figure out what the closest node is? Well, we need the list of nodes that we're considering still. And we need the distances that give you the meaning of closest. So that's A. And then B is mark all of its unmarked neighbors with blah, 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 blah. We'll just leave that method. So let's say mark. We know the node that we're marking the neighbors of, and we're going to mark it into this array of distances. And oops. And C is remove it from the list. So here I'm actually going to write some code just because I know what that is. Do some array manipulation here to subtract that closest node from the list of unchecked nodes. Oops. All right. We say that, and of course this is going to fail because we haven't defined anything, but let's just verify that that's the only problem. Yeah, failure undefined variable or method initial distances. So what we have here is we have a kind of a skeleton of an algorithm that might work. And we have some tests ready for it, feature tests. But for now, we don't want to run these tests. So we're going to turn them into pending tests. And now we're going to go into it and implement all the details of the things that we think we need to make this algorithm work. So the first thing is this initial distances. And remember, that is supposed to be marking the goal with 0, and everything else is still unmarked. So how can we do that? Oh, we gotta write code, we're doing tests here. There's going to be a method initial distances. So let's give it a simple case. I'll say if we give it node 0, or node A, it labels that. Well, it's so obvious, I'm just going to write. I'm basically writing in English what I'm about to type here. I expect that if we do maze.initial distances.
You need a goal? You need to pass it the goal?
I guess we need to pass it a goal. So let's do that. Put it over here. We know we're going to need that. Say we give it an A.
It's a little more obvious then.
All right, now it's a little more obvious. So if we pass it an A, what do we want? That's my phone fuzzy, sorry. If we pass it an A, we want to have a 0 in the first position because that's where A is in the array. And we want everything else to be unmarked. So this is how we want to start. This corresponds to the, where you just put the 0 down on the goal in that slide before. That array was, that's the equivalent of that. We just put a 0 in the goal position. So I'm saving it and see if it passes. Undefined method initial distances. And remember, what we always like to do is just return the answer.
You did initialize.
Oh, yeah. That's the danger of doing that.
You're a little too hippie.
Yeah. Okay, so it's still failing. That's the problem. Wrong number of arguments.
Yeah, to equals. You use curly braces instead of length.
Oh. Yeah, this is the problem with this new syntax. I have to put it all in one line.
No, you can put a parentheses and you make parentheses across all.
You can put the .2 on the next line.
Parentheses.
Okay.
I like the equal.
Yeah, Jason said you could put the .2 on the next line.
Yeah.
Seems like a good
All right,
choice.
so now it's passing, but obviously that's not good enough. It's not. We're not actually doing what we want. And so to force that code, let's say we pass in a D. We know that everything should be nil except the last element this time, which should be 0. And that fails because it just got the same thing that we wrote. And it just got the thing that we stuck into that initial distances method. So now we've got to actually write the method. And I'm going to kind of do it step by step here. We have, so let's say I start with just a bunch of nils. I do this array just containing a nil and multiply it by the length of the nodes array. That'll just return a bunch of nils. And I can set, well, let's see, if I set the first element of it to a 0, I have to return the array. So this is kind of back to replicating this initial thing where it's just returning 0, nil, nil, nil. Because I just put in 0 here. Here we really want to put in the goal. But goal is a symbol, and we need an index into this array. We can find that by doing nodes.index. That finds the position, the index of goal in the nodes array. And now our test passed. So we have initial distances.
You could make distances a hash, by the way. I would totally do it that way. But
Right.
if that's your plan, go ahead.
We'll think about that the next time. Kind of short. 2 minutes to go. All right, so let's go on to the next method we need to define. We need this closest method. So write a spec for it. And so how does that work? We call closest with a list of nodes that we're still checking. So let's make a really simple case here. Like say we just have A left, and the distance to A is 0. And that's all we're doing. Then we really want that to equal A, because what else could it be, right? It fails because there's no method closest. Closest needs to take nodes and distances. And still fails, probably because we should haven't given it exactly what it wants. Now all the tests pass, and you see my thing catch up there after. Well, it says they all passed here. The little thing in the corner should catch up in. So again, we need to write another example. So let's make a more interesting one. Like we have 0 and say we have all of the nodes. But let's just have 2. 2, and we have 0 and nil. We still want it to return. Oh, it's still going to pass. Let's do it like this. We have 2 nodes, and distances nil and 0. In that case, we would want to return B, because B is the only one with the score. So that fails. Actually, thinking about it, that's going to be a little bit harder. I don't want to bring nil into it yet. Let's put a 1. Okay. Expected B got A. So how do we make this code actually work? Well, it turns out there's a method called min-by, which you can use. You refer to David's table of the enumerable modules, which will search for the minimum element of the array according to a value returned by a block. And the value is the score of the distance. So we want to find the distance of that node. But again, node is not a number, it's a symbol. So we have to do that node.index thing again.
You have distance versus distances.
So now all the tests pass. And this is almost right. But I want to write a test involving nil. So let's expand it out to include a C. And let's put a nil in here. I think that'll already just fail. And what's the failure? It says comparison of nil class with 0. We tried to do this min-by. They've got to somehow internally min-by is using the less than or greater than or something like that, and it's applying it to nil, and that doesn't work. So I think I can just put an or 10,000 here. That'll probably effectively exclude all of the nils, because if it's ever nil, it'll return 10,000 and it'll find something else instead. Now the test passed. I think that's good enough for closest. Make sure your maze is not bigger than 10,000 or not. So now we have one thing left to do, and that's the mark method here. That's kind of the most interesting one. That's where it's actually doing the work. So let's see how that's supposed to work. Well, if you look at the code, you'll notice mark is expected to actually change what's in this distances array. Some people might not like that, but it makes the code pretty short in this case. So I'm going to make an example here. Say we have the 0 and nil, nil, nil for my distances. And I call maze.mark. Oops. And obviously we're going to be marking the only node there is to mark at this point, which is A. And passing the distances array. After that, we should expect distances to equal 0. And if we go back to what our simple maze looks like, if we have a 0 here, the next step is to put a 1 here on B. So we should expect to have a 1, nil, nil, nil.
Misspelled describe though.
Alright, so now it fails because we have no method called mark. Do our usual thing. We know we want to just return the expected value here to make this test pass. Oh, it still failed. Alright, someone see the problem here?
Yeah, you're not actually returning a change to distance.
Oh yeah, of course. So let's do that totally differently.
Distances dot replace. Dot replace.
I'm just going to say distances 1 equals 1.
Yes, that's one.
So now I've mutated distances. I've put a 1 in position 1. It passes the test. And that's a little more useful than what I was doing before because it's actually, that's actually kind of what our ultimate algorithm is going to look like. Let's do something more complicated. Say I start with a 1 and I mark it. We want to have a 2 in that position. But we're just marking it with a 1 by default, so what we got is 1, 1 instead of 1, 2. So, well, we can just say its distance is 0 plus 1. It's a little bit closer to the real algorithm. And that passes. Let's make something a little bit harder again. So we're doing a different node. I guess there's no other simple node here. But I'll put a 0 over here. And mark that one. So now we're going to expect, remember, the node, D node is connected through to here and to here. So both of those should get 1s. And of course that's going to fail. It's actually trying to add nil to something because it's just using this index 0 by default. We know how to find the index of a node. We have nodes.index node. So that slightly changes the failure. Now it found it, but it stuck the 1 that it computed into position 1 of the array, and everything else is still nil. Because this 1 is just totally invalid. So what do we actually want to do? We want to get all of the neighbors, which comes from that connections array. Connections array is a hash. We can just access it like that. We get each of the neighbors. And then we want to stick the neighbor in here. And again, we need this index thing. It's going to suggest a refactoring soon. So this will go over all the neighbors and mark, oops. What did I do? It's totally dead. I have some, I need to do.
Yeah.
All right, so now it passes, and I think this is actually the correct algorithm. So let's go back here and unpend our pending tests. 2 failures.
Oh, no.
What happened?
Maybe you didn't return anything?
Maybe not. Yeah, expected to get some lists. See that it says expected to get 2110, we got nil. So David was right, we forgot. We didn't actually write our algorithm correctly. We have to return the distances at the end. So 2 failures. So there's a little subtlety that we didn't think about. See how there's some 3s in here and some 2s where there shouldn't be? What's happening is it's overwriting the old values. Back in our we didn't actually have enough cases. I'm gonna go back and unpend this, append this again. Make one more spec on the mark spec here, mark description. Imagine we started with 0010, or let's put to make it a little more valid. I'm gonna say we do something like this. We want to keep the 5, and we want to put a 6 over here. But this 1, if there is a 1 there for whatever reason, you shouldn't overwrite it with a 6, which is what the algorithm would do. And if you look at that, see it does overwrite it with the 6 right now, because we're not checking for that. We're just overwriting everything in this loop. The way you can do that is next if there's already something defined. And so that passed, and now I think maybe it's good. Also, I'm out of time, so.
Terminal.
Yeah, that's true. Okay, everything passes.
Yay.
Do I still have 5 minutes?
Yeah,
for
there's
discussion?
5 minutes for discussion.
All right.
Then we should start. Yeah.
So basically, that was my idea about how you could implement an algorithm where you know the algorithm. You don't have to discover the algorithm through test-driven development. You just write it down and then proceed to write the code you need to implement it. What do you think?
I think that was great. That's much closer to how I would write a real algorithm.
Alex?
I like that approach in general in that you have an idea, you know how it's supposed to be solved because it's a known algorithm, and you're trying to build well-tested software. I would say that the specific way that you tackled it, you automatically kind of fell into, because you have an algorithm which is kind of a function, you kind of fell into this defining out the function and then saying, breaking it into smaller functions that still work on all these things. I would challenge you to think of maybe in your solve that was your outer kind of layer. Maze is what you made Maze do is play with all of these different things in different ways. And I would say, if you look at, for example, unchecked nodes equals nodes, and then you have this thing later where it's like this function closest takes unchecked nodes and distances to figure out what the closest node is, and Maze is responsible now for figuring out what the closest node is for a set of nodes. If you envision unchecked nodes not as just a copy of this collection, but as a totally different class that might be a collection style class that knows how to find the closest,
Yeah.
and still do exactly what you did, but not do it at the method level, but say, create all these other objects that you want to use, and then test drive out those objects, that would be a more desirable object-oriented, test-driven approach.
One reason why I'm going to sort of follow on what he's saying, one reason for that is mark closest and initial distances.
Does that have nothing to do with the maze? Right?
Well, it's not that it has anything to do with the maze, but the way you've constructed this class, those are in fact private methods that wouldn't actually be tested.
Yeah.
Right? If instead you envision what they're doing as collaborating objects that have a public interface, now they become a thing that you can test, irrespective of how they're used in the solving of your maze problem.
Yeah, when you
Right.
say if you want to test a private method, it's a good sign that it should be private.
Correct. Well, no.
That it probably belongs on another class.
Right.
Yeah.
If you want to test it, it probably belongs on another class. It's a collaborating object.
If it's a detail to the class to the system on your test, but you feel like you need to test it, that's a sign that there's a thing there to extract into a testable thing.
So I totally agree with what you were trying to do here, and I like it a lot. I just think if you do an analogy to, let's say, if you're going outside in on, say, a web application that everyone in here is probably fairly familiar with, where if you view solve as like your controller action, right? And if in your controller action you immediately just create a class that does stuff, and then you then drive out the test beyond that class, very similar here. If you look for the objects that you want to play with and create them in solve and tell them to do things, and then test them out, it creates a little bit better structure.
I think from the standpoint of, given that you already know what the shape of the algorithm looks like, right? But you haven't actually built out in Ruby the ways you're going to solve the problems that the algorithm needs solved for it. This works as a way of driving out what the